Hey everyone, welcome to my channel. Subscribe for more such content. If you haven't subscribed yet, please subscribe. Without further delay, let's get into the video. What is recursion? Function calling itself is recursion. Calling multiple times and working on the same thing helps us to do in the form of recursion. Recursion can be implemented in four patterns. So let's understand pattern 1, which is in forward manner, printing 1 to n. Here the function I comma n, I is 1 for us and n is 5. Let's suppose that's an example. If 1 greater than n, which is I greater than n, then we are going to terminate the function, which is not. 1 is not greater than 5 here. We are going to print 1, I. Increment the function. Call the function and increment the I value. I plus 1 comma n, which is 2 comma 5. 2 greater than 5? No. And again print I2. Similarly, it prints till 5, after which 5 plus 1, 6. 6 greater than 5, which is true, because of which we are going to terminate the function there. And after which we are going to return the output, which we have got none other than 1, 2, 3, 4, 5. At 6, we have got it terminated. So that is the termination point at which we have got it terminated 6 comma 5. Let's proceed with pattern 2 now. Printing n to 1 in forward manner itself. What we are going to do here? Same function calling I comma n. We are going to check the condition whether I is greater than 1 or not, which is 1 is greater than 5 or not. If it is, we are going to return. Else we are going to print. What we are going to print? N minus I plus 1, which is nothing but 5 minus 1 plus 1. It gives 5, right? So prints 5. We are going to call the function I plus 1 comma n, nothing but 2 comma 5. So 2 greater than 5? No. 3 greater than 5? No. 4 greater than 5? No. It continues till 6 and continues to print 5, 4, 3, 2, 1 as n minus I plus 1. A simple formula which would be used to print from backward direction. So here it gives the output 5, 4, 3, 2, 1. Let's proceed with pattern 3 now. In here we're going to backtrack. Implemented in backtrack manner and going to print from n to 1 rather than 1 to n. That's a printing mistake in the heading. So calling function I comma n, I greater than n, which is not true in the initial step itself, as 1 comma 5 are the points which we have considered. Function I plus 1 comma n, 2 comma n, then 3 comma n, then 4 comma n, then 5 comma n, after which 6 comma n, as it satisfies the condition above which none of those satisfied. 6 comma n, which is 6 comma 5, has satisfied. Now we are going to backtrack, printing I values, as we have got 5, 4, 3, 2, 1, as we are going to print from the backward direction. See, that's the pictorial representation in which we are going to backtrack and call again, because of which it helps us to print the values which we got. It gives the output 5, 4, 3, 2, 1. Let's proceed with pattern 4 over here, backtracking. The backtracking manner which prints in 1 to n. So let's just get into the function I comma n, in which we are going to check whether our I value is greater than n or not, which is not true. Now we are going to increment I value, which is 2 comma n. 2 greater than 5, either of it is not false. 3 greater than 5, not. 4 greater than 5? No, it's not. 5 greater than 5? It's not either. 6 greater than 5? That's true. So we are going to terminate the function and we are going to backtrack because the function hasn't ended it. Print n minus I plus 1. Here our n value is 5, I value is 5 plus 1. So it prints 1 and backtracks again, prints 2. Backtracks again, prints 3. Backtracks again, prints 4 and again to print 5. So our output would be 1, 2, 3, 4, 5. So the 3 and 4 headings are a little mistaken. If you understand all these 4 patterns, then you'll be able to work on recursion pretty quickly and easily. So here's an example for recursion, which is Fibonacci series, in which we are going to check whether our value is equal to 0. If it is equal, then we are going to return 0. If it is equal to 1, then we are going to return 1. These two are base conditions in our Fibonacci series. So the tree represents how we are going to call the functions in Fibonacci series. We called n minus 1 and n minus 2 helps us to call Fibonacci of 3 and Fibonacci of 2 in case of Fibonacci of 4. This Fibonacci of 3 and Fibonacci of 2 should be further called by more of it unless it reaches 1 comma 0, which are base conditions. And so that is the ideology. Fibonacci of n minus 1 plus Fibonacci of n minus 2 helps us to work on this Fibonacci series. The time complexity 2 per n and space complexity is big of. Let's understand one more example for recursion, which is factorial. In this, we are going to call just one chain, a linear chain, which is factorial of 5 helps us to call factorial of 4. You know factorial, right? Factorial of 5 is nothing but 5 into 4 into 3 into 2 into 1. So function calling, we are going to pass integer n. The base condition would be if our n is equal to 0, then we are going to return 1. Else we are going to call the condition and implement n multiplied factorial of n minus 1. Here the factorial of n minus 1 calls again factorial of 4 and again factorial of 3 and again factorial of 2 and again factorial of 1 unless our base condition has been reached. So that is a linear representation. 0 factorial is 1, 1 factorial is 1, 2 factorial would call 2 multiplied factorial of n minus 1, which is 2 minus 1, 1. 2 multiplied 1 is equal to 2. Similarly, the factorial of 3 would help us to work on 3 into 2 into 1 factorial of big of n. Let's understand multiple recursion. Here we are going to consider an example of Fibonacci series giving input as int n as parameter. If n is equal to 0, return 0. If n is equal to 1, return 1. These both are base conditions for Fibonacci series. Else we are going to return Fibonacci of n minus 1 and Fibonacci of n minus 2. Addition of these two values helps us to work on the whole series. The main ideology of whole Fibonacci series is Fibonacci of n minus 1 plus Fibonacci of n minus 2. The tree is such an example. If we call Fibonacci of 5, n minus 1 would be Fibonacci of 4, and n minus 2 would be Fibonacci of 3. It continues until we reach the base condition. So let's understand the calling tree in depth, step by step. Fibonacci of 5 helps us to call Fibonacci of 4 and 3 as of n minus 1 and n minus 2. 4 helps us to call n minus 1 and n minus 2 again. 4 minus 1 is 3, 4 minus 2 is 2. Similarly, Fibonacci of 3 helps us to call Fibonacci of 2 and Fibonacci of 1. Here, Fibonacci of 1 has reached the base condition which returns 1 for us. n. Fibonacci of 3 helps us to call over here again the multiple recursion as we said. Fibonacci of 3 calls Fibonacci of 2 and Fibonacci of 1. Again we have reached the base condition. Fibonacci of 2 helps us to call Fibonacci of 1 and Fibonacci of 0. Both of those has reached the base condition. Again, in Fibonacci of 3, we have called Fibonacci of 2 and Fibonacci of 1, right? The Fibonacci of 2 and Fibonacci of 3 calls Fibonacci of 0 and Fibonacci of 1, which is the base condition all over again. The Fibonacci of 2 and Fibonacci of 3 in the left has also reached the base condition. So all of the left and right nodes of the Fibonacci of 5 has reached the base condition here. So here the table helps us to understand the call order. First we call the Fibonacci of 5, which helps us to call Fibonacci of 3 and Fibonacci of 2 in recursive manner. Then Fibonacci of 4, then Fibonacci of 3, then Fibonacci of 2. At last Fibonacci of 1, which will be a base condition for us. Later on, Fibonacci of 0 is also a base condition for us. Both the left and right nodes of the Fibonacci of 5 has reached the base condition,